we're ready to start. Are you okay with that, David?
Yes, let's go.
Okay, great. Hi, everyone. As I just said, my name's Andrea Wetzel. I am the Senior Research Program Manager for Events, Workforce Development, and Education at the Critical Infrastructure and Resilience Institute. And I'm going to just briefly talk a little bit, very briefly, about the DHS Summer Research Team Program. And then I am going to turn everything over to our director, David Nickel, to introduce our speakers today. As I said before, this program is, or this talk is from our DHS Summer Research Team. And they have been working all summer, or for 10 weeks this summer, on putting together a research project along with their mentor, David Nickel. The purpose of the DHS Summer Research Team program is to increase and enhance the scientific leadership of minority-serving institutions and research areas that support the mission of DHS. Faculty that are early in their careers, along with one or two students, are selected by DHS for the program. It is a competitive program. The team then conducts research at one of the 9 DHS University Centers of Excellence or their partner institutions for 10 weeks during the summer. During a normal year, DHS provides a stipend, housing, and travel expenses to the faculty and their students. And then the COE, or the Center of Excellence, normally provides a faculty mentor, an office space, and then other amenities as we can to the team. This year, the program was held virtually, so not all those things happened, unfortunately. Let's see, the Summer Research Team is sponsored by DHS Science and Technology Directorate, Office of University Programs. For the past 4 years, CIRI has hosted summer research teams. We have hosted 2 teams from Benedict College, one from the University of Texas, El Paso, one from Southern University A&M at Baton Rouge, and this year our team is from the University of Houston downtown. CIRI has hosted 5 teams that have included 5 faculty, and we've had a total of 8 students. To add to the program, CIRI works very closely with the Granger College of Engineering at the University of Illinois to provide extra educational programs to help the summer research team students grow in their research abilities and have some professional development time. I would really like to add that we really enjoy working with this program and hosting it for the last 4 summers, and honestly, we get more out of the program than anyone will ever know. So, anyway, David, you'd like to go ahead and introduce the team?
Good, thank you for passing along the talking stick. So you might have noticed this is a very different summer than in the past. And the impact for me is that I've been able to mentor this team, whereas in the past I did so much traveling in the summertime that we would other faculty doing that largely. But this time I got to do it. In fact, I met with the team so often that my own graduate students, I think, were starting to get jealous. So, see how that plays out. But I'm delighted to introduce them to you. We've got Dr. Shengli Yuan, who received his PhD in MS in computer science from the University of Texas at Dallas. He worked in networking for a while before joining University of Houston downtown, and he's a full professor, senior member of IEEE, and very well embedded in the networking community. Tuba Hashmi got her very recent PhD degree from University of Houston downtown. She will be staying to do a master's degree, and she reports in her report to the DHS that this was a formative summer for her as far as thinking about doing research and sticking with our graduate studies so that she could do research in computer science. And we're glad to see that we have had that sort of impact. Now, these folks, Kingley and Tuba, no doubt have been saying, would these people stop talking so we can start talking? And so we'll say, now is your opportunity to start talking. So without further ado, Kingley and Tuba.
Thank you very much, David, and thank you, Andrea, and also thank you everybody for attending today's presentation. It's a privilege and it's an honor to be here and meeting with everybody virtually. So this year, our project is the investigation of security weakness and vulnerability in Internet of Things routing protocol and solutions. And the first part of presentation will be done by Tuba, and then I will take over to talk about the rest of it. And so, Tuba, are you ready? Can you go ahead?
Okay, sure. Well, hello everyone, and like Professor Yuan said, thank you for coming today. We're just going to get started. So for our introduction, basically IoT, Internet of Things, is an emerging technology. It's changed the way people interact and communicate on the daily. In fact, according to a Gartner study, IoT connected 4.9 billion things, and by the end of 2020, so the end of this year, it will be connecting 25 billion things. And because it's such an expansive and extensive network, the objects that connect to it are susceptible to various security exploitations. As a safeguard against these attacks and exploitations, it's important to remember the various components of cybersecurity and protocol measures. The routing protocol for low power and lossy networks, also RPL, is standardized for routing in WSNs and IoT device networks. In this research project, we focused our effort on researching the protocols and vulnerabilities within it, and hope to further this research in the future on alternative routing protocols. Some of the common IoT applications that we hear of every day are wearables, such as your Apple smartwatches or your MISO gesture controls. These have the capabilities to read your heartbeat, to track your steps, and connect to other e-health applications. E-health applications are connected health applications. They basically offer a means of mass data collection, and they pave the way for smart medical devices. Other common IoT applications include smart cities, and cities like Dallas and Denver are part of these. They basically make a city more efficient by using IoT devices to solve complex problems particular to the city, like water management, waste controls, emergencies, and so on and so forth. Another very common IoT application are smart grids. They basically use information and from the behaviors of electricity suppliers and consumers in the automated fashion industry to improve the efficiency, reliability, and economics of electricity. And I found that very interesting during my research. So next we have the IoT application architecture. So basically there are three layers to this architecture level. The first and the lowest layer is perception, and the goal of the perception layer is to collect data from the physical environment and convert it into analog input into digital form, which is suitable for transmission. The second layer is the network layer. It's responsible for processing the data with the help of various networking topologies. And this is actually the layer also responsible for the routing of data. The third application is the application layer, and it provides interface for IoT devices. As the topmost layer, it actually has the responsibility to connect the user and the application. But one of the most important things to note is this tri-layered architecture does not have the capability to transmit large amounts of data without exhausting energy consumption. And the energy consumption is far beyond what is possible for an IoT device with its resource constraints, lack of infrastructure, and limited physical security. So that's like one of the big vulnerabilities that we did our research on. Next, we have RPL, which is the routing protocol for low power and lossy networks. So basically in this RPL, IoT devices are connected using mesh and tree topology to build a direct destination-oriented directed acrylic graph. And this tree or graph characterizes a tree-like structure that indicates default routes between nodes. And the node can be associated with multiple parent nodes, and the destination nodes are known as sinks versus the senders are known as senders, and they provide routes to the internet and the routes. And then an RPL enabled network has the prospective data rate, which is low, but the communication is prone to high error, which also leads to a high energy consumption. Some of the constraints are that internal memory constraint. Basically, it's unable to run sophisticated operating systems, algorithms, and protocols. It has a computational capability constraint as well. It's unable to support complex routing algorithms and encryptions, which make it susceptible to like hacking, as well as power constraints. So energy consumption is one of the most important areas related to improving RPL. Energy consumption in RPL is actually handled by a trickle timer. And this trickle timer is very ineffective in a dynamic environment because it results in high energy loss and failed packet delivery. These are some of the known vulnerabilities and attacks dependent on topology and traffic. So for example, you have sub-optimization, isolation, eavesdropping, which is like sniffing and traffic analysis, as well as impersonation. So identity attacks such as Sybil attacks and clone ID attacks. During a Sybil attack, malevolent nodes falsely cast messages with different and fake IDs, and these cause working nodes to also transmit and pass on those false messages. This false node spoofing, if you so call it, takes up memory space and presents nodes to be fully connected when in fact they are not connected. Another example of vulnerability in IoT devices is interdependence. So for example, an IoT device can implicitly be controlled by conflicting rules and behaviors. One example of this is like a smart thermometer, such as a Nest, if you guys have it in your houses. Basically, you can set it so if it detects overheating, it can open windows of the house, but it doesn't take into consideration the risk of security. If nobody is at home and the windows of the house are open, that's a risk on security. And so it needs to be smart enough to recognize that. And then when you have a large system or a device, it can also be compromised by outside interference because lightweight IoT devices, like we talked about, do not have the memory management unit for complicated encryption methods. And now I'm going to hand it over to Professor Yuan to explain a little bit more about our project. Professor Yuan?
Thank you, Tuba. So the primary problem we are trying to investigate is we focus on large and dense LT networks. And the reason is that well, with the growth of the IoT network, and we foresee that there will be more and more devices joining the IoT networks, therefore making the network large and dense. So far in the research communities, there has not been a whole lot of research in that area. So that's why we want to focus on that. And then more specifically, we want to find out exactly how that constraint on the memory size will has impact on the security and the vulnerability in the context of a large and dense network. And also the power consumption's impact. So as Tuba mentioned, the memory size constraint and the power constraint, as well as CPU power constraint, is a major constraint on the IoT devices. So those constraints prevent the devices from running some sophisticated programs and algorithms and the protocols. But we want to know more precisely how those constraints will play a role in security. So that's the two major problems we are trying to investigate. Go ahead, next slide. So in order to assist us with the research, we use simulation programs. So we look at two simulation programs. One is called Contiki/Kuja, and then the other one is called Simulus. And Contiki is an operating system. It's open source operating system for IoT devices, and it has been around for quite a while. And the Kuja is the simulation environment. And so the advantage of this simulation software is that it actually simulates from the perception layer all the way to the application layer. It actually runs the actual code that runs on the IoT devices. And it supports a larger number of different IoT devices, such as the Z modes, such as Sky modes, so on and so forth. And so that's the Contiki and the Kuja simulator. And we also look at another simulator called Simulars, which is based on Python. And so after comparison and study, we decided to use the Contiki/Kuja as our main simulation, excuse me, as our main simulation program, and use the Simulars as the backup. And then we build a network of various size with various memory constraint. And then we look at the behavior of the network and also the nodes. Next slide, please. So our investigation have the following findings. So the first is that the constraint on the internal memory, and more specifically allocated for the router's routing table and the neighboring table, have a significant impact on the RPL tree's ability to converge. So the routing table in a router basically tells a router where to forward a package when a package arrives. So the router will look at the package destination address and then go to the routing table and then find out where to forward that package. So that's a routing table. And so in an IoT network, the router need to have an entry for every possible destination in the network. And so that is in the storing mode. And then there's also a non-storing mode, which means that the router does not keep any entry in the routing table. Instead, all the packages will be forwarded to the root node or the sync node. And then the sync node will decide how to forward the package. And then the sync node will put the entire path insert the entire path to that package. And we call that source routing. So that's about the routing table. And the neighboring table is in every router. Basically, it records who are the neighbors. Okay? And so we record basic information about the neighbor, their MAC address, their IP address, the link status, so that later on when the packet arrives, it knows it work together with the routing table and forward that packet to one of the neighbor. And then our research find out those two tables specifically has very significant impact on the RPL tree's ability to converge. So I'm going to talk about that in more detail in just a minute. And another finding is that the CPU power consumption is significantly higher in the nodes with many descendant nodes than the nodes with less or no descendant nodes. And so, for instance, if there's a node that has many children and children's children, and so there's going to be a lot more CPU power consumption than the node, for instance, in a leaf node. And so there's security implications. So we are going to talk about that as well. Next slide, please. Okay, so more specifically, how the constraint restrict the router's ability. So as I mentioned, in the storing mode, each router must have an entry for every possible destination in the IoT network in the routing table. Now, because the the size of the table, the memory size allocated for the table is very limited in the IoT device. And so if the network grows and grows, become dense and large, and so the router, if it's in storing mode, the router may actually exhaust all the memory allocated for it with all those possible destinations. And so by default, in Contiki, okay, by default, the size of the routing table is 10 entry. So which means that you can only have space for 10 possible destinations. Okay? And so if the network size grow bigger than that, so in the storing mode, then the IoT will not be able to, the IoT router will not be able to have an entry for all the possible destination. Okay? And so when the network starts, this causes the RPL tree not to converge, because in order for the RPL tree to converge, all the nodes information will eventually has to be delivered to the root, and so the root will register the node to be part of that tree. Okay? Once the routing table gets exhausted, the nodes, the intermediate nodes, okay, will stop forwarding that information to the root. So the root will never get the information about the nodes, that all the nodes in the tree. Okay. And so that's the constraint on the routing table. Now there's another constraint which is on the neighboring table. As I said, okay, a router must have an entry, must know all the information about all of its neighbors. So it has to know the IP address, the MAC address, the link status, so on and so forth. And all those information are stored in the neighboring table. Okay? In order for the router or node to forward any information or communicate with any neighbor, and it has to have entry in that routing, the neighboring table as well. And so by default, once again, by default in Contiki, it's 10 entries there. So which means that every node maximally have 10 neighbors. Of course, that number can change. We can increase that number, but still there's a limit because for most IoT devices, the internal memory size is less than 1 megabytes. So therefore, there's always going to be a limit. You can increase the size to 100 entries, for instance. But when the network becomes dense and large enough, eventually those routing table and the neighboring table will get exhausted. Okay, next slide, please. Okay. And so therefore, once the table get exhausted, and so the routers, okay, will not be able to either recognize additional neighbors, okay, or not be able to forward information of additional nodes to the root. Okay? So, which in both cases, the RPL tree is incomplete, and the sum of nodes are disconnected from the tree. Next slide, please. Next slide, please. Okay. So that was the case with yes, this. So that was the case with the storing mode. Now the IoT does support a non-storing mode. In that case, the router actually does not work as a router. It's just a regular node. It has no, it does not have the routing capability. And so the routing table is in the root. Okay? So if a node receive a packet, and the root does, if the node receive a packet, that node does not attempt to forward that package along the optimal path. Instead, it simply forward that package all the way to the root. And then the root device has no constraints on the internal memory or power. So the root has a big, large routing table, and it has an entry for all the possible destination for all the destination, entry for all the destinations. And so the root will take the package, look at destination address, and then build entire path from the root all the way to that destination. And then the root will insert that path, that complete path into the packet, and then forward that to one of the neighbors. And the neighbor will just look at the path and then forward along to the next neighbor. So those nodes, except the root, do not do any routing, except just looking at the complete path in the package and then forward to the next neighbor. So that's in the called non-storing mode. That is not the default by in the Kentucky operating system, and even though it does not have the impact, the issue with the limited routing table, but this one rely on the source routing. So all the package will have to go to the root and get routed by the root. So therefore, it's not efficient, and also there's power consumption issues, which I'm going to talk about next. Next slide, please. Now, here are some of the preliminary sample data that we collected during the simulation, and the complete data will be presented in a paper that we are going to publish. So in this table, we have networks with one sink node and also 35 sender nodes, and all of them are in the storing mode. Now, the 35 node network is not considered to be very large, even though it is larger than most LT network these days. But it's still not terribly large. And the reason is that it takes very, very long time to do the simulation, because as I mentioned, that simulator would have to run the entire operating system from the device driver all the way to application. So therefore, take very, very long time to run the software for all the nodes. So we choose 35 node network, but we change the memory size for the neighboring table and also the routing table. So we make them very small. So therefore the effect is the same. Compared to the size of the memory size of the routing table and neighboring table, a 35 node network is by comparison by relativity is still very large and dense. And so here's our data. So if we set 3 maximum entries in the neighboring table and the routing table, and in a 35 node network, and we got 0 nodes added in the tree. So which means that that tree is empty. Now, if we change the neighboring and the routing table size to 5 entries, so after we run the software for a while, we have 6 nodes in the tree. Now, if we make the size to be 7 entries in the neighboring table and the routing table, and after we run it for a while, we get 32 nodes in the RPL tree. And if we use 10 maximum entries in the neighboring table and the routing table, then we have all 35 nodes in the tree. So here we can see that when the constraint on the memory size allocated for neighboring table and the routing table is very, very strict. In this case, 3 or 5. Okay? Well, only very small number of nodes in the network is included in the RPL tree. Okay? The majority of the nodes are outside the tree. Okay? So if there's a package coming in from outside the IoT network trying to reach one of those destinations, it will never get there. Okay? So that's one problem. And go to the next slide, please. Tuba, next slide, please. Okay, so here is the another table. So this table has the CPU power consumption, okay, which is the ratio between the non-RPL root nodes with the most descendant and the one with the least descendant. So as you can see that, okay, in a network with 1 sink and 10 senders, so relatively small network, okay, the CPU power consumption ratio is about 3.2. So a node with a non-root node with many descendants, with most number of descendants, compared to the leaf node, the power consumption is 3.2 times. If the network grow to bigger, in this case 20 senders, 1 sink node and 20 senders, then the ratio becomes 3.4. And then in a 30 nodes sender network, it becomes 3.9. And if in the 40 node sender network, become 4.3. Okay. So the bigger or the denser the network becomes, okay, the more power consumption will be for the nodes that with many descendants. So this is in the storing mode, which means that the other nodes, okay, are serving as routers. So therefore, they are going to forward their packages along the optimal path whenever that is possible. Next slide, please. So this is also a power consumption ratio table, and then this is non-storing mode, which means that all the nodes would forward their packages to the root, and then the root will decide how to forward the packet to the destination and use source routing. Okay, so all the nodes except the root does not perform any routing. So the data shows in a small network with 10 senders, 1 sink, the power consumption ratio is 3.0, and then for 20 nodes, it becomes 3.4 times. With 30 nodes, about 4.9, and with 40 nodes, 40 centers, it becomes 16.9. So the power consumption ratio in the non-storing mode seems to be much higher than the one in the storing mode. And we think the reason behind that is because in the storing modes, the packages are forwarded by the nodes along the optimal path. Okay? It doesn't have to go all the way to the root. And so therefore, many packages will now go through many nodes because it can go to a node, then the node maybe find, okay, this is one of the destination is one of the neighbor. So therefore, immediately follow that neighbor. Doesn't have to go all the way to the root. But in the storing mode, all the packages will have to travel to the root first, and then get sent down to the destination. So every node, especially the ones that which many descendants, would have to forward many more packages, and also look into the source routing information. So we think that's the reason why the storing mode, in the non-storing mode, the power consumption ratio is much larger. Of course, we are going to look into the data in more detail in our complete paper. Next slide, please. So what is the security vulnerability with our investigation? Okay. So there are some very interesting vulnerability here. Now, compared to some of the vulnerability that have already been identified by the research community, okay? In those cases, many of those attacks are performed by malicious router, okay, injecting some control messages. Right? So we call that more of an active attack. Right? And so the attacker node, the malicious node, has to be somewhat sophisticated. It has to understand the control package, the format, and what the functionality of the control package, so on and so forth. So it has to be somewhat smart malicious node. Okay? But the issue that we have identified reveals some very interesting vulnerability. Okay? So here they are. So when the IoT devices are in the storing mode by default, okay, so we know that the constraint on the internal memory, okay, may severely hinder the RPL tree's ability to converge in a large or dense network, okay, even without any attack. Okay. So once the network size itself becomes large enough, okay, part of your network will never join the RPL tree. Okay, so therefore the root will never be able to forward packets to those destinations. And so that is an issue on availability. Okay. Now, if somebody wants to do an active attack, okay, so the malicious node, all the malicious node need to do is to spoofing MAC address and IP address. Okay. It doesn't have to know anything about RPL protocol or the control message or the interaction of those control messages. All you need to know is just send out multicast frames, okay, that with spoofed MAC address and IP addresses, right, with many spoofed MAC address and IP addresses. Okay. And those addresses, once those packages get received by a neighboring node, and then those neighboring nodes will have to register those addresses in their routing table, in their neighboring table, right? Because their routing table and neighboring table are so small in size, and so those tables get exhausted very, very fast. And once that get exhausted, okay, then those nodes will stop accepting any new nodes into the RPL tree. So therefore, they cause the RPL tree to be incomplete and disconnected. So this attack is very, very inexpensive, very, very easy to carry out. And then another vulnerability is that power consumption, as we mentioned. Okay? So once again, even without external attack, okay, the nodes that with many descendants, okay, will consume the power much, much quickly than the nodes that have zero or very, very little number of descendants. Okay? So once the power is out on some of those nodes, then your network gets disconnected. Okay? So those are all the security issues on availability of the network. So we propose the following solution. Okay. So first is to limit the number of nodes in every tree below the capacity of the neighboring table and the routing table. Okay. Or on the other hand, okay, increase neighboring table size or routing table size, okay, whatever that is possible. And then the root in every tree serve as a proxy for all the nodes inside the tree. Okay. So all the data will get stored on the root. Okay. And so if there's need to access those data, okay, it does not have to go all the way to the node. Instead, the root can provide those data, and the root does not have a constraint on their power and memory or computation capability. So therefore, that free the rest of the IoT nodes from those constraints. And then the root are equipped with much more resources, and so they can communicate with each other with more advanced and secure routing algorithm and protocols. So the root would be communicating with each other using some more sophisticated routing protocol, okay, instead of that RPL. And now, of course, the detail we have to look at the detail. So we haven't been able to figure out the detail yet. Okay, next slide, please. So conclusion and the future work. Okay? And so in this study, we confirm that the constraint on internal memory and the power supply create significant security vulnerability. Okay? And we understand specifically how the routing table and also the neighboring table restrict the RPL's tree's ability to converge, and therefore has a create issue for the availability. And then we implement, and for the future work, which we are going to implement and test our proposed solution. And also we want to expand our research on network reliability issue, which is related to security, but also is very important aspect of IoT network. Next slide, please. Okay, so this project is a wonderful project. It's a great project. We really enjoy it, and we want to thank Dr. David Nico for his guidance and insight throughout this project. Without his leadership, this project would not have succeeded. And we also want to thank our student assistant Jeremy Mink for his dedication and hard work. And we also want to thank Dr. Beth White of Auris, and also Ms. Andrea Wetzel of Critical Infrastructure Resilience Institute, and also everybody else who have helped us and support us through this project. So it's really a wonderful project, and we hope to have the opportunity to continue our collaboration in the future. Okay, so that concludes the discussion. Are there any questions? Any questions? Oh, of course. If you have any question, you can email us and or email Tuba, and we would love to discuss and any issues, any questions related to this project. Thank you very much for attending. Okay, I guess that would be it then.
Thank you very much.
Thank you.
Thank you both.
I do.